The first 1,000 collectors are in orbit, not satellites in the old sense, passive machines serving one function. These are precision solar surfaces, each one a thin mirror-bright structure placed with calculated care in a shell around the sun, each one feeding harvested light into a distribution network that, for the first time in the history of any species on any world, begins to feel like something more than planetary. The energy output is measurable. The architecture is working. A civilization that has spent its entire existence drawing power from its planet is, right now, at this moment, beginning to draw it from its star. The structure that would make a civilization effectively immortal by giving it access to its star's full energy output is also, by the same physics that makes it work, the largest Kessler trigger ever conceived. And the more completely it is built, the more certainly it destroys everything orbiting the star it was built to harvest. What the energy readings do not show at 1,000 collectors is the gravitational interaction table. Not because it does not exist. It does. It has been computable since long before the first collector was placed, but because at 1,000 objects the interactions are manageable, the perturbations are tiny, and the timescale for drift-driven orbital intersections is measured in centuries. 1,000 collectors is not the threat. 1,000 collectors is the down payment on a system that will eventually contain more individual gravitational bodies than there are stars visible from Earth on the clearest night. And that number is where the mathematics of what the structure does to itself stops being manageable and starts being irreversible. Exactly how that transition happens, the specific mechanism by which 1,000,000,000,000 coordinated objects convert themselves into an uncontrollable debris field, is the calculation that every popular explanation of the Dyson swarm has consistently omitted. Every object in orbit is being pulled in multiple directions at once. The star at the center provides the dominant pull, but everything else nearby is also pulling, all the time, at forces small enough to ignore for years and large enough to matter over decades. A single satellite orbiting Earth drifts slightly because of the moon, the sun, the oblateness of the planet itself, and the gravitational tug of every other satellite in nearby orbits. Operators correct these drifts with small propulsive maneuvers, routine work, inexpensive in fuel, entirely manageable at the scale of a few thousand satellites. The drift itself is not the problem. The scale at which the correction must be applied is what changes everything. A Dyson swarm at meaningful stellar coverage contains somewhere between 1 trillion and 1 quadrillion collectors, more individual objects than there are stars in the entire Milky Way galaxy. Each of those objects is a gravitational body. Each one is pulling on every other one, simultaneously, continuously. The sun's pull dominates, but Jupiter, the solar system's largest planet, exerts a gravitational influence on every inner orbit object that is not negligible across the centuries a civilization expects its primary energy infrastructure to operate. Saturn adds its contribution. So does Mars. So does Venus. So does the mass of the swarm itself, distributed across its orbital shells, pulling inward on its outer layers and outward on its inner ones. The accumulated effect of all of these forces on any single collector's orbital path cannot be calculated exactly. Not approximately, exactly. Henri Poincaré proved in 1890 that no mathematical method exists to solve the gravitational interactions of 3 or more bodies with perfect precision for arbitrarily long future times. That proof has not been overturned in the 130 years since. The swarm is not a system waiting for a clever orbital mechanics solution. It is a system whose behavior was proven to be unpredictable at the precision required to prevent collisions before anyone began building it. Approximations exist. You can track 1,000,000,000,000 orbital paths forward through time using numerical simulation, running the calculation in small steps, predicting where each object will be a fraction of a second from now, then another, then another. These approximations are excellent. They are also accumulating errors with every step, and over decades of continuous simulation for 1 trillion objects, those errors correspond to real uncertainty about where the objects actually are. At some point in that uncertainty window, not in the worst-case scenario, in the expected outcome of the perturbation dynamics, two collectors whose paths were predicted to safely miss each other do not miss each other. The collision between two swarm collectors is not a slow event. Objects at Earth's orbital distance from the Sun move at roughly 30 kilometers per second, the same speed the Earth itself travels. When two of those objects meet at that relative velocity, the energy released at the impact point is equivalent to several tons of high explosive per kilogram of mass involved. A collector that weighs a few hundred kilograms, lightweight by engineering standards, designed to minimize the launch or manufacturing cost, delivers the energy of a small battlefield munition at the moment of contact. The debris produced does not drift. It sprays outward at velocities high enough to cross the neighboring orbital shells within minutes. Each fragment carries enough momentum to do to the next collector what the original collision did to the first two. And the neighboring orbital shells are dense. They were designed to be dense, because density is coverage, and coverage is the energy output the whole project was built to provide. Here is where the accumulation rate matters in a way that has no comfortable analog on Earth. In an orbital environment with one object per million cubic kilometers, a debris fragment might travel for years before it statistically encounters anything. In a swarm dense enough to intercept a meaningful fraction of stellar output, the average distance between collectors is measured in kilometers or hundreds of kilometers, not millions. A fragment ejected from a collision at 30 kilometers per second covers 100 kilometers in a little over 3 seconds. The debris cloud from the single two-collector impact reaches the density of the surrounding swarm within minutes, and the collisions it generates there produce new debris that reaches the next shell within minutes of that. The propagation front does not wait for the civilization to respond. It is already in the next shell before any alert has been transmitted, assessed, and acted upon. You are the engineer monitoring the swarm's collision avoidance network when the first alert arrives. The location is in the inner orbital zone, where the swarm is densest and the energy yield per collector is highest. The impact event timestamp is 2 minutes old, the time required for the alert to propagate through the coordination network to your display. In those 2 minutes, the debris front has already traveled 3,600 kilometers in every direction from the impact site. The neighboring collectors in that radius are gone. Their debris has extended the front further. Your display is showing a pattern that does not look like a single impact event. It looks like a zone that is erasing itself. The question the alert doesn't answer, the one that matters more than the collision coordinates, is where the front will be in 12 hours, and whether there are any orbital paths that do not pass through it. The answer most engineers would reach for at this point is also the answer that the swarm's designers would have built in from the beginning. Autonomous propulsion on every collector, continuously correcting orbital drift before it accumulates into collision risk. This is not a speculative technology. Modern satellite constellations at Earth orbit perform automated avoidance maneuvers as a matter of routine. The software exists. The propulsion systems exist. The logic that it scales, that a sufficiently advanced version of the same technology handles 1 trillion objects the way current systems handle tens of thousands, is the intuition that makes the swarm feel solvable. What that intuition does not account for is the energy arithmetic. Correcting a single collector's drift requires fuel, which requires energy. At one collector, the cost is negligible. At 10,000 collectors, it is an operational budget item. At 1 trillion, the total propulsion energy required for continuous orbit maintenance scales not linearly with the number of objects, but with the square of swarm density. Because denser packing means more objects perturbing each other more frequently, which means more frequent corrections, which means more propulsion energy per unit of coverage. Double the swarm's density to double its energy output, and the maintenance energy cost quadruples. Triple the density, and the maintenance cost multiplies by 9. At full civilizational scale, the density at which the swarm captures a significant fraction of the star's total output, the propulsion energy required to keep the swarm intact consumes a fraction of the swarm's own power production that grows with every collector added. The civilization is not drawing unlimited energy from its star. It is drawing energy from its star and feeding a growing portion of that energy back into the machine that keeps the star energy machine alive. The coordination network that generates the maneuver instructions carries its own arithmetic. To prevent drift-driven intersections, the network must model the gravitational state of every collector continuously and generate correction commands faster than the perturbations develop. For 1,000,000,000,000 objects, each interacting with every other, the computation required to run that model at the fidelity the correction system needs exceeds what the laws of thermodynamics permit any physical information processing system to achieve within the swarm's operational footprint. This is not a statement about current computer speeds. It is a statement about the minimum energy any computational process requires to manipulate information, a limit that applies equally to silicon processors, optical computers, and any other architecture that operates under the same thermodynamic rules. The network cannot be built fast enough to prevent the drift, and the energy it would require to try rivals the energy the swarm produces to fund its construction. The two constraints together, propulsion energy scaling and coordination impossibility, do not produce a solvable optimization problem. They produce a trap with no exit at full density. Reducing density to bring the maintenance cost into budget proportionally reduces the energy harvest that justified the project. Reducing density to the point where the coordination problem becomes tractable produces a swarm that harvests a fraction of stellar output too small to qualify the civilization as Type 2 by any meaningful definition. A sparse Dyson swarm is not a degraded version of the original concept. It is a different concept with a different purpose, wearing the same name. In 1991, researchers extending Donald Kessler and Burton Corpellet's original orbital debris modeling applied updated collision probability calculations to Earth's then-current satellite population. The study was specific in its methodology. It modeled the growth of debris density as a function of satellite population density and collision cross-section, and it projected forward with conservative estimates for launch rates. The finding was that Earth's orbital environment could reach the threshold at which collision-generated debris produces new collisions faster than natural orbital decay removes fragments, without any additional launches, purely from the debris already present and the projected near-term additions. That threshold was not a distant theoretical limit. The study placed it within decades for the most densely occupied orbital zones, even with the atmospheric drag that naturally decays low-orbit debris within years to decades. The inner orbital zones of a Dyson swarm have no atmosphere below them. An orbital debris fragment produced at Earth's orbital distance stays at that distance indefinitely. The self-sustaining debris threshold at Dyson swarm density is not a projection. It is an entrance condition. The point at which intervention becomes impossible does not arrive when the entire swarm is destroyed. It arrives when the debris density in any connected orbital region exceeds the threshold at which a maintenance vehicle entering that region generates more debris than it removes. At that density, every object sent into the affected zone, every collector, every correction vehicle, every replacement component becomes part of the debris field before it completes its mission. The civilization does not lose the ability to intervene when the front is large. It loses the ability to intervene the moment the debris in any one zone crosses that specific density, because the geometry of orbital mechanics connects adjacent zones, and the front expands through those connections faster than any response can contain it. Freeman Dyson proposed the swarm concept in 1960 as the logical infrastructure of any civilization that survives long enough to exhaust its planetary energy resources. The proposal was correct in its identification of the resource. The sun's energy output is real, it is vast, and capturing it is physically possible. Dyson's calculation established that a civilization with sufficient manufacturing capacity could, in principle, produce enough collector surface area to intercept the full output. What the proposal did not include was the gravitational stability analysis for the resulting trillion-body system in a solar system that already contained 8 planets. That analysis was not conducted in the 1960 paper. It was not included in the subsequent 60 years of popular treatments of the concept. The omission is consistent across textbooks, science communication channels, and long-term civilization planning documents. And it has persisted not because the analysis is impossible to perform, but because performing it produces a result that ends the conversation. Every design retreat that makes the swarm orbitally stable makes it energetically insufficient. Concentrating collectors at the gravitational Lagrange points, the zones where objects can maintain stable positions relative to a planet without continuous correction, captures a fraction of total stellar output too small to define civilizational capability. Using short lifespan collectors with planned deorbit before they drift requires a manufacturing and replacement program that must produce and place collectors continuously at rates that scale with swarm coverage, drawing on an energy source that is not yet the swarm that is being maintained. Distributing fewer, larger collectors at wide orbital spacing produces a structure that harvests single-digit percentages of stellar output and calls it a Dyson swarm only by analogy. Any orbital infrastructure, the habitats, communication relays, manufacturing stations, and propulsion depots that a civilization operating at stellar scale would place in the inner solar system for the same reasons it built the swarm, occupies the same orbital volume as the collectors when the debris propagation front reaches full density. The failure does not happen in empty space. It happens in the most inhabited, most technically complex volume of everything the civilization has built, and it converts that volume into a debris field at the same orbital velocity that made the swarm's energy output possible. The civilization that achieves stellar energy extraction and the civilization that triggers this failure are not two different civilizations. They are the same one at two different points in the operational lifetime of the same structure. Gravitational perturbation in a multi-body system does not become less severe with more advanced technology. It becomes more severe as the number of bodies increases. And the Dyson swarm requires the number of bodies to be as large as physically necessary to intercept the target fraction of stellar output. Any civilization at any technology level in any star system with multiple planets building any orbital collector structure at the density required to qualify as Type 2 on the Kardashev scale faces the same orbital dynamics calculation. The density required and the density at which debris self-propagation becomes self-sustaining are not two separate variables that can be independently optimized. They are the same variable measured at two different thresholds, and the swarm's purpose requires it to operate above both of them simultaneously. Every long-term colonization architecture that treats Dyson-scale energy as the foundation for interstellar missions, the propulsion budget, the construction budget, the communication infrastructure, is drawing on the energy the swarm produces only during the window before the debris propagation front crosses the self-sustaining threshold. That window is set by the swarm's density, the perturbation accumulation rate in its orbital environment, and the timescale of the first drift-driven intersection. All three values are calculable. Whether they leave the civilization enough time to disperse beyond the inner solar system before the window closes is the question that every treatment of the Dyson swarm as humanity's obvious next step has not answered and not asked.